Welcome guys. Considering this particular course here, which is Math 312, with course title Real Analysis 2. The very first thing we need to consider in this course title is what we call the series of a function, the sequence and series of a function. So let me take the first one, which is sequence, sequence of a function. So this is the first thing that we want to consider for this first topic. So you have this particular section here which says sequence of a function. I would like to give a very clear explanation to this. So I would like to give the definition. What do we mean by sequence of a function? So I can easily give you a definition which says, let me try to reduce my pen. So a sequence, let's just say a sequence of function. I think that's what we want to define, right? A sequence of function is a sequence is a sequence whose stem whose stem are in terms of a function. That's all. That's just the simplest definition we can give them. So and this sequence of a function can actually be denoted in different form. Is that we use un to denote sequence of a function, or sometimes we can actually make use of xn to define the sequence of a function. At times make use of an to denote sequence of a function. We also have other denotation. We can also use Sn to denote this. But for the sake of real analysis 3, I think that should be real analysis 3, sorry for that. So for the sake of this real analysis 3, we are considering this particular denotation. What we must get familiar with us is Fn, small letter f, then Sn. So Fn precisely, that's what we always make use of in this case. So this is what we want to make use of. Okay, so this is a sequence of a function. So I can actually give you an example. The sequence of a function, let's say fn with a variable of x in terms of x, I can have it as n open bracket 1 minus n x squared. So this is the what? Sequence of function given to us. Okay, this sequence of function given to us. We use fn of x to denote that. So since we already have this in that case, likewise we also have series of a function. So for series of a function, you are going to use the same definition. Just follow it up. A series of a function. A series of a function is is actually you can just say it's a series. Is a series whose terms are functions. There's no need for us to talk more on that. So I can actually give an example to this. So in this case now, we can have something of this nature. Let's say we have a series, something like this, of a function in this format, where you have your n starting from, you can actually have a first term. You can have n start from 0 to infinity. It's taken of that. So that's how it works in that case. So to write this clearly, you have to put in terms of x there. And then I believe that looking at this now, you are trying to find the summation on x on n itself, not on x. See, let's assume that we have something of this nature now. Let's say our sequence of function is given. Our function is given as this. This is our function here. So that means the sequence of function, I can try to put it in a bracket this way. So this is the node sequence of the function. And then looking at this, for the series part, that means we can actually have it in this format whereby is a series, okay, whose terms are functions. So the function here, let me take this function. Let's say we have n open bracket 1 minus n x squared. That means I'm actually trying to find the summation of this expression here with respect to n. So if I want to solve something like this, that means I should have summation of n times 1, which is n, minus n times n squared, that's n squared x squared in the bracket. So I still have the range for all n start from 1 to infinity. So looking at this now, I can split it up. The summation of a plus b can still be equivalent to summation of a plus summation of b. So you can actually apply it here too. That's summation of n here minus summation of what? N squared x squared. So looking at this now, I can try to have summation of n here because I have n start from 1 to infinity where n is included. And then in this case, I can actually take any other letter aside from n to be a constant. X squared will come outside from the summation. So I'll only be left with n squared. So as far the summation is depending on n starts from 1 to infinity, the range is on n itself. So that's how it works in that case. So after this, then we need to consider what we call the pointwise convergence. Pointwise convergence. So when do we say that a function is said to be pointwise convergent? So I think that will be the next thing I'm going to explain in the next um, video.